Thanks for the kind introduction and for the invitation. It's a pleasure to be here. So it's like my second time in Seoul, but first time I was just like really fast. I'm really enjoying my time here. So thanks for the invitation. So from the title of the talk, you may be wondering what elasticity and hydrodynamics has to do with like theoretical physics and even with modern physics. Because every time we think about like hydrodynamics and elasticity, we may think that this is a problem that has been solved, or at least formally has been solved like more than 100 years ago. And I'm saying formally because, okay, we don't know if we can solve Navier-Stokes equations, but that's another issue here. Okay, so, but well, yeah, let me just start, but just like motivating the problem and just posing some sort of like general sort of like statements about how we understand physics like currently. Okay, so basically I'm just starting with this like statement. I say what is it all about, or what I'm going to talk about here, and how do we understand physics? Well, we right now we know that everything is just all about scales. Okay, it depends at what scale you are going to observe the system, and then we have a sort of like a certain general principles that are based on symmetries that we use to construct the theories that we believe are going to describe nature. Okay, and within all this sort of like a set of like what I said is kind of like general knowledge. It's like, well, first we have learned that like symmetries are really a powerful tool, and we try to understand every physical system in terms of symmetries. Okay. Another important thing, at least like for field theories, is like the fact of like a locality. So the more symmetry is something that we know, that the more symmetric the system is, then it's the easier it's going to be, the less parameters we are going to need to describe it. Something like is like really important is like all the ideas that are coming from RG flows, which is like basically, so if we want to see the system for like from a very close perspective, from the microscopic, so then that's the system is going to be sort of like a mess. There may be like too many degrees of freedom, but the farther we start just like moving or to the lower the energies we are going to describe, the less degrees of freedom are going to be relevant, and well, that's a very important aspect of like when we are going to construct effective theories. It's all about finding what are the relevant degrees of freedom that are important for our system. Okay, and in the case of like finite temperature systems or like finite density, somehow kind of like a thermodynamics is kind of like this sort of like extreme low energy regime in which like basically nothing happens, everything is in equilibrium. It's like this super boring state that but the thing is that fortunately almost everything we see around us are just systems that are parametrically close to that state that I'm calling thermodynamic states. And in particular, these things are things that we call liquids, gases, solids, and yeah, well, that's kind of the story. Okay, so now I use one to compare liquids, gases, and solids. What are the differences between them? Okay, and I'm showing like this like cute video because somehow one of the goals of this talk or this research program is just to be as clever as that dolphin that can play with vortices. And the question is, can we be as smart as them and understand how vortices behave and what to do with them? Okay, so then let's start comparing solids, liquids, and gases. I'm just like showing here 3 examples. Okay, so from some perspective, I mean, from a very qualitative and generic perspective, these 3 systems are not like that different in the sense that okay, we know that we have some gap excitations in gases, liquids, and solids. We know that we can propagate sound. And then from that perspective, we would say that, well, they are not that different, okay? But then we may say, okay, well, but look, as I'm showing here on liquids, you can have like this sort of like vortices, but in gases we also can. And then my question is, what about crystals? Okay, do we have an analog of like a vortex in crystals? And the thing is that indeed, indeed there are. So I'm going to be like, later on, I will be slightly more precise. And for example, I mean, so this is like an hexagonal lattice, and here yours, I'm just like, as you can see here, I have substitute one hexagon by a pentagon and another one by a pentagon, and I'm going to argue later why that thing is a vortex. Okay, but actually, there is something that I kind of like omitted when I mentioned the similarities between these three systems, and is that actually a solid is a system that possesses long-range order. Okay, actually, a crystal is a system in which translational invariant has been spontaneously broken. Okay, so if there is a system that I should compare with a solid, it should be a superfluid. Okay, and a superfluid is a system in which like an internal symmetry is spontaneously broken. So in the solid, as I'm going to argue, or as it is well known, so a solid is a system in which translational invariance is spontaneously broken. Okay, what I'm showing here is like picture of a superfluid, a rotating superfluid. This is just like a cold atom systems, like in a trap that is rotating. So, well, and these dots are precisely vortices that form in the system. Actually, the funny thing with these people, what experimentalists do to create these things in the labs is just that they just trap all these cold atoms at some sort of like high temperature. They give angular momentum to the system, and they just start cooling down the system, slowly cooling down, and then once you cross like the critical temperature in which you have like the phase transition to the superfluid phase. So since you are in a superfluid phase, the system cannot rotate, and then the only way the angular momentum of the system can be supported is like via the formation of vortices.
Do you know which atom is helium or?
Yeah, I don't know exactly which atoms, but I think they play with like no, it's not helium. It's not helium. So they use in the case of cold atoms. I mean, I think they use like more heavy elements, but I don't know particular which ones they use. Okay, a bit more about examples of liquid solids to see somehow the range. I mean, the variation in scales where like the physics of like liquids, solids, and manifest. Okay, so here I just have a picture of the sun, which we know that is like some sort of plasma. Then like the interior of Earth is like, okay, the Earth is a rocky system, so it has like solid part, some part that is kind of like liquid. So again, picture of like the atmospheric dynamics. So here, this is like a very interesting phenomena that is like the way it's understood currently. So this is Earth, this is Pacific, okay? And this red, this sort of like a red region is the responsible actually of the El Nino atmospheric phenomena. And actually the way it's understood is actually like this is a topological wave. Okay, this is a topological wave. Does this system people understood that it somehow behave as some sort of like a topological insulator, and here like and the equator is kind of like the boundary, and then you can have like the formations of these like topological waves, and then this is like a very stable wave that it generates like in this side of the Pacific, and it propagates all the way up to basically up to Ecuador in South America. Okay, this thing here is just like the picture of some experiments on graphene sheets, okay, where the electrons show, I mean, the experiments have like shown that that there is some, that electrons actually behave hydrodynamic under certain conditions inside a material. This is the characteristic picture of what is like the output of the collision of heavy ions. In this one is from Rick, I think, if I remember properly, okay, which is basically when you collide heavy ions, there is a phase that is called quark gluon plasma that forms in the system, and actually the quark gluon plasma behave as a I mean, the equations that describe the dynamics in some region is before the let me call it, what is called freeze out, when basically this fluid evaporates. This phase is described by a set of hydrodynamic equations. And well, here, this is kind of like a graphene sheet that is solid, and this type of like a rotating superfluids that I was mentioning, that interestingly, if those superfluids bubbles rotate fast enough, then vortices form a lattice, and those lattices behave as a solid. Actually, the effective theory that describes that phase of matter is some sort of elastic theory. Okay, so let me just start kind of like introducing hydrodynamics in the simplest possible way. I think this formulation of hydrodynamics is the simplest way we can talk about. Okay, so this is a formulation of hydrodynamics, just like introduced by Landau, and it starts from sort of like we assume that we have a system that is close to thermal equilibrium. Okay, so then, well, we suppose that we have like some internal energy. S is just like the entropy of the system, and the density, and okay, and if this fluid is just like flowing, let's say, so then okay, this momentum and the conjugate variable, that's velocity. Okay, so then what he did is just basically postulated a set of like Poisson brackets, non-canonical Poisson brackets between the densities. Okay, so between the variables that we are going to understand as hydrodynamic variables that are going to be precisely the conserved densities of the system. And basically this bracket, what it's just telling us is that P is just the generator of space translation. For that reason, P with N, give me this quantity. So then P has to act on any density in this form because it just generates translations. Let me resume. Sorry. Okay, what I was just coming back to the argument, what I was saying is that basically you postulate this set of non-canonical Poisson brackets that basically this is just like the diffeomorphism algebra. It's just saying that the quantity P that is momentum has to generate translations in the system. Okay, and my relevant variables then are just like density and momentum, and the equations of motion. So then I just postulate it to be just like time derivative of the density has to be just the bracket between and sorry, this here, this H should be just the energy density. Okay, that I'm assuming is a function of like those variables there, and then by just computing the Poisson brackets between the density with my equation of state, basically that is H, that should be epsilon, then this Poisson brackets then just produce Euler equations of hydrodynamics. Okay, so of course that's we know that that's not it, because hydrodynamics is a theory, it's a dissipative theory. Okay, so somehow we have to modify that construction such that we incorporate entropy production in the system, because as I mentioned, hydrodynamics is a dissipative theory. Okay, and well, just like this textbook, and you follow the textbook, it tells you what do you have to do to construct your hydrodynamic theory. And the whole argument is just basically you assume so that the existence of like some local current that you call entropy current, and you postulate as some sort of like a local version of the second law of thermodynamics, requiring that the divergence of that current has to be always positive. Okay, and that constraint, and in addition, you modify your constitutive relations, and by constitutive relations, I okay, yes, I think I should just continue. Yeah, sorry. Yeah, the point is that so the statement is just like these equations conserve entropy, so then you postulate the existence of the second law, whose divergence has to be positive, and then that will constrain the things you can add in your hydrodynamic equations in some like important form that I will show immediately in the next slide. So the statement is that just by modifying this previous statement, by adding these just two requirements, is just enough to fully constrain whatever is allowed by symmetry in your hydrodynamic equations. So the example that I'm showing here, okay, is the case of a relativistic theory, okay, with a U1 global symmetry. So from the perspective of Landau, or even in this previous case, so in the end, the equations of motion of hydrodynamics are just the conservation equations of the system. Okay. The reason why the conservation of equations of the system are the hydrodynamic equations is because hydrodynamics is about precisely describing a system that is close to thermal equilibrium. So we really care about really low energies in which we are just in regimes which are perturbing the system, and we are just interested in the long wave regime of those perturbations. Therefore, yes.
Because I'm not familiar with this hydrodynamics, but at least now I see this equation, and if like this eta, zeta, sigma, if they are zero, they look very familiar. But of course, if they are non-zero, now the equations are more complicated.
That's correct.
Yeah, I want to understand just the physical meaning of these parameters, like eta, zeta, sigma.
Yeah, if you give me 30 seconds, I will be there. Okay. So yeah. So the point is that what I was just trying to argue is that in the dynamics of the system, the statement is that the dynamics of the system has to be just determined by excitations that are associated to conserved quantities. Okay, because every other excitation that is associated to a non-conserved quantity in the long, at very late times, it should just vanish, it should decay, and only the conserved quantities are the things that are going to determine what's going to happen really at late times. Okay, so that's the reason. Well, Hydro is just about like fixing the set of equations. Here, this F, I'm assuming that I have some external field that couples to the current J. So then basically this term here in the right-hand side is just telling me it contains basically the Lorentz force and what is called Joule's heat, basically. So the transfers of energy and momentum from the sources into the system. Okay. So then what else? Well, let me just forget, as you mentioned, about these parts in the team you knew, and you said that was familiar. Well, yeah, that was familiar because that's just an ideal fluid. Okay, that's an ideal fluid. Actually, this is just like a covariant version of these things. Well, energy is the energy conservation equation is not written here. Okay, but if you plug this team you knew and the energy momentum conservation, you split indices. That's basically the equation of motion. Okay, so in other words, what I'm just like trying to argue is that, that without this part, this is what we call the ideal stress energy tensor. Okay, all this part of the stress tensor contains no dissipative terms. That's the whole statement. And similarly with the current, this thing sigma is what we will call conductivity. And so then it means that if you have somehow an electric field that is equal to that part, so you don't have dissipation, or in absence of electric field and zero gradients, or sigma zero, so then this is just like the non-dissipative part of the current. Okay. So the whole story is that then hydrodynamics basically is understood in terms of a derivative expansion. So okay, we assume that we have like some ideal description where anything depends on gradient. There are no gradients dependence on the hydrodynamic quantities that now I'm saying that are basically chemical potentials and the velocities and temperature. Okay. And then you just start, when you have your ideal theory, you modify your T mu nu, you modify your ideal part by everything that you can add containing one derivative, acting on the variables, which are chemical potential, temperature, and velocity. Okay. You construct that, you construct the entropy current, you impose that entropy current has to be positive, and that constrains these coefficients, eta, zeta, and sigma, to be positive. So entropy production just tells you that conductivity has to be a positive quantity, and these two things here are viscosity. It's what we call viscosities. This term here is what is called shear viscosity, that is associated how when you do shear deformations of the fluid, how the momentum transfer in this perpendicular direction happens, and this is associated to compression in the fluid. That's the reason it's called shear bulk viscosity. Okay. So then, yeah, that's the interpretation of these two things. So these things generate entropy. They're associated to, and in fact, if I plug these things here, so those are the relativistic Navier-Stokes equation. Okay. So is it like clear now?
What is this vector E?
The electric field of that thing. It's just basically F contracted with the velocity. It's like the commobile. It's a commobile electric field. It's F mu nu u nu.
So it has a derivative expansion.
So this is truncated at first order. So this is first order hydrodynamics. Yeah. If you may go like higher orders in derivative if you want, but then the number of transfer coefficients grow really fast.
Okay, so E is derivative expansion of the potential, vector potential.
Yeah, it's the electric field. So it's just F mu nu u. So it's the contraction F with U. So it's like this like commobile electric field.
The next one, T and P mu rho.
Well, P is just a transverse projector to the velocity. So yeah, you have the Minkowski metric. So or your metric, and with the velocity you construct a transverse projector to the velocity. That's what P is. This thing, this
mu plus G mu. That's the projector, no?
Yes, you're right. Yeah,
It's the same.
Yeah, it's the same thing. Yeah, it's the same thing. Now there is like a funny story here. It was like a funny story that happens like more or less at the end of like the decade of the 2000s. Is that, well, when people was like super excited about the ADS-CFT and were computing everything they could from holography. These two papers appear more or less at the same time, computing in some holographic system the constitutive relations using like this fluid gravity correspondence story. And they were using some particular model. And when they compute the constitutive relations, they found a term like that in their constitutive relations. And if you recall, in the current, the only thing I had in my current was just like this electric field term. Okay, there wasn't anything like. Well, let me show again. You see, and velocity, conductivity, electric field, and nothing like that. Okay, and so at the moment, like this is Piotr Surovka. He was like he's one of the authors in this paper, but then he was at the same time in Washington with Son, and rumor said that Son immediately wrote the authors of the papers telling them what you are doing has to be wrong, and it's like it's not in Landau's book. Okay, this term is not in Landau's book, has to be wrong. What is like the point is that Piotr and Son were in the same place, and they managed to solve actually the issue with that paper, where they proved that it's not only, I mean, that actually those papers were not correct. Sorry, that the results on that paper were correct. And actually just using hydrodynamic arguments, they prove that if you are describing a system with chiral, like what we call now a chiral fluid, a system made of chiral fermions, those terms has to be there. And it's just like, if the system has an anomaly, this curl of this vorticity term in the current has to be there. And in addition, they found that there has to be some term also proportional to the magnetic field. Okay, the coefficients in front of this vorticity and the magnetic field are directly connected to the triangle anomalies of the system, and they have to be there.
What is V? It's vector field. What is V? V.
Why the magnetic field?
No, what is V?
V.
Yeah.
Well, it's just the velocity, but the space part of the velocity. It's just the curl V is the vorticity. So I will show in covariant form the expression now. Okay. So then the statement is the following. So if you have a current that is anomalous, I mean, if you have like a global symmetry, U1 global symmetry that is anomalous. So we know that in 3+1 dimensions, there are two triangle anomalies that we can have, which is like basically this one that we call like gauge anomaly, that one we call mixed gravitational anomaly. These two coefficients here, CA and CM, are just coefficients that are just basically determined in terms of the amount of left-handed minus right-handed fermions we have in the system. So they are just like sort of universal numbers. If the current that we are taking into consideration suffer this sort of like quantum anomaly, then the constitutive relations for the currents that I wrote before need to be modified in this form. So by curve V, I mean, so this thing. So this is the quantity that appears in my, and this is so that's what I'm calling, that's my covariant form, right, in the magnetic field and the vorticity. So in other words, my constitutive relations for the currents are just modified by these coefficients that I'm calling sigma B, V, and these things. And
Like delta J.
well, the correction. So it's what I wrote before, the term with electric conductivity, and I have to add this to my previous current. Okay, and then this thing here, I'm just calling it J epsilon, which is basically the T0I part of the stress tensor, of the stress energy tensor, which also received contributions from the anomaly. Okay, that's the exact values of those coefficients. They take this like super simple form. Okay, what is like really interesting is that, so this thing here contains 4 derivatives, because these are Riemann tensors, contains 4 derivatives of the metric, but this one contains 2 derivatives. And if you are doing first order hydro, these equations, the divergence of the current possesses 2 derivatives. This one possesses 2 derivatives. This thing has too many derivatives, should not play any role in the dynamics. Okay, it should not play any role in the dynamics. So it should actually, in principle, actually, this Sons and Surovka paper, they didn't find anything related to that. Okay, the result basically contains this term with CA, which is this coefficient, this term here, this term here. The thing is that, well, okay, this paper of them had like a huge boom. A lot of people started studying this problem, like here myself. And the thing is that we were, and the question was like, how is it possible that this thing does not, I mean, it's kind of like universal. Hydrodynamics tells you that sigma B has to be just this coefficient times mu, okay? Independently, it seems that it does not care how the system, what are the microscopics of the system, coupling constant, does not care about it. So well, people started just computing these things at quick coupling, just via Kubo formulas, all these conductivities, computing in holography where the coupling constant is supposed to be like infinite. In all these cases, the results were agreeing. But then in that paper with my collaborators, then we actually, by computing literally these transport coefficients using Kubo formulas just for free fermions, we found that actually these two conductivities, that this is the vertical, you see this is called chiral vertical conductivity because it's the one that appears. So you have vorticity in your system is your rotating, and you have a current that is parallel to the vorticity, completely weird. And that thing has a term that goes like t squared, and the coefficient is this coefficient. Okay, and as you can see also like here. So then not only this gauge anomaly coefficient determines the form of this transport of the transport coefficients, also the mixed anomaly. And then we study what happened in holography, and somehow right now it's understood that
I think some systems where the anomalies on the boundaries are cancelled by the anomalies in the bulk or vice versa. But how about that? So is the story only concerns the bulk, or do we need something on the boundary?
So here we don't have boundaries.
So everything is in bulk.
Here we don't have boundaries. This is like a 3+1 version, but for example, if we consider something like I don't know, quantum Hall problem that we know that we have edge plates, which is basically a 1+1 chiral fermi. Okay, that system has a gravitational anomaly, and this famous sort of energy current that goes like t squared.
No, the quantum Hall is the chiral, not gravitational.
It has a gravitational anomaly. Yeah. So 1+1 chiral fermions have a gravitational anomaly. Okay, and then that so in 1+1 you have that due to that gravitational anomaly you have like the boundary, you will have a current, an energy current that's going to go t squared. That's just kind of like related to that.
So in this case, everything is in bulk.
Yeah, I mean you can imagine that as the boundary of a 5-dimensional topological insulator or something like that.
My question is, so we have delta J, then does it mean that we have a vortices in the bulk?
It's vorticity, no vortices.
Then
so it's just imagine that you have just a fluid, you give angular, so you get this fluid rotating like rigidly, and then you will see a current that is proportional to that.
Yes, so then the vortices used to be due to some low energy limit of some Heinrich theory. Then what is this vortices about?
Let me just make a distinction. I'm not talking about vortices, I'm talking about vorticity. Okay? Just imagine that you have your cup of coffee, you put your spoon and you start just like, if that coffee was a chiral fluid, and you start just like you give like angular momentum to your fluid because you are shaking it like in circular form, you separate the charges in your coffee. That's what this effect is telling you. So it's just vorticity, not vortices. Okay, so that phenomenon I'm talking about is expected to be relevant in the quark-gluon plasma. Okay, temperature is like much higher than the quark mass, so then in principle quarks are like massless. Magnetic field is like some magnetic fields are generated during the collision. It's very large, but actually just like finding a convincing data from those systems is like really hard. Okay, it's really hard. But the thing is that actually in the condensed matter, so in solids, there are some materials that are called Dirac and Weissman metals, where the electrons behave actually like Weyl-fermions. They just behave like a chiral system. And once those materials were discovered, so then people immediately said, okay, we should see this chiral magnetic effect in those materials. And indeed, all these materials have shown this type of behavior. Okay, let me just, since I'm kind of like been talking about these things like for a long time, let me just mention about this experiment. Okay, so this is just like this is a slab of a material. So in this region, basically, they're injecting a current, so there's an electric field, and there is also like a magnetic field. Okay, so then they have electric and magnetic field that are parallel. So then via the current anomaly, that should just like pump some kind of imbalance of left-handed and right-handed fermions in the system. Okay, now after you sort of like pump this like imbalance in the chirality of the system, so you have like the whole slab, this thing should just like diffuse, or this like sort of like a chiral charge should just like diffuse throughout the system. And now in this other regime, they just have a voltmeter and a magnetic field, no electric. Okay, so since there is a magnetic field here, the chiral magnetic effect tells you that there should be the charges should just like separate in that other region here, because okay, well, this chiral charge is just like spread over the sample, and here you have a magnetic field that tells you that they should split. Therefore, the voltmeter should show some value, non-vanishing value, and what this is kind of like what this thing is telling. So this is like the magnetic field here, and this is the resistance. Okay, therefore you see that there is like a drop in the resistance with the magnetic field. Don't ask me about this part that I don't understand very well. This is kind of like an indirect, these things are related to an indirect measurement of this chiral magnetic effect. But the thing is that you can prove that that if you have electric and magnetic field that are parallel in a sample, so the conductance of the sample grows like the square of the magnetic field, which is what is seen here. So this is the inverse, which is the resistance, and that's the reason it's just like dropping. But the thing is that you can reduce what is called the magnetoresistance of a system that is like a chiral, which is in a vial or Dirac semi-metal by putting electric and magnetic field parallel. Okay, so I will just now move into the business of superfluids, and I will introduce them in the most heuristic way possible. And I will do that again, just like playing this Landau game. Okay. And basically what I'm just going to say was like, let's just introduce a field that is conjugate to the charge density that is going to be my Goldstone field. So now I'm postulating, and I postulate that I have this bracket, theta n equal delta. Okay, and my equation of state, so then it's just a function of, my energy has to be a function of the density, and it has to be a function of the gradient of theta, that's basically what you call superfluid velocity. Okay, and well, you compute your equations of motion as before, and well, your equation tells you that the time derivative of n has to be just the divergence of j, and you get this equation that is like what is called Josephson relation, that tells you that the chemical potential of the system is the time derivative of theta. Okay, and I'm going to argue in a very hand-waving way how do you introduce like particle vortex duality. That is something that typically is useful in superfluids. That is just like basically I have just my energy. Let me just like Legendre transform this quantity, and instead of like working with like energy, introduce like some sort of Lagrangian. Okay, I'm just calling. So I'm calling V the gradient of theta. Okay, I'm just redefining this gradient of theta V, and I'm using mu is just the time derivative of theta. Okay, and the point is that by take this Lagrangian by introducing Haber-Stratonovich, or doing a Haber-Stratonovich transformation, basically you can just rewrite this Hamiltonian new variables, okay, where basically now this current, so this current has been is interpreted as some electric field, and this and the density as some magnetic field. This is just obtained by understanding, we're in 2 + 1 dimensions, sorry, by the way. So this equation here can be just understood as Faraday's law. What I'm just trying to say is that this equation can be understood as Faraday's law in 2 + 1 dimensions, which is in that case, the magnetic field is only scalar. And if you solve this equation as a Bianchi identity, then you can, instead of using theta as a degree of freedom, then you can use like some gauge fields as degree of freedom. And what is like important here is that when you do that, the singular part of the theta field and the singular part or the non-single value of the field theta, that is what you will call the vortexes in the superfluid, will appear as this thing that I'm calling rho omega and j omega, which is like the vortex current of the system that is coupled precisely to this gauge fields, where this thing is just like the A0 and this thing is like the space part. Okay, so the statement is that that you can sort of like dualize a superfluid system, and in the dual picture, so the object that your phonon somehow is just going to be captured by some gauge field. Yes.
But the 2+1 gauge field, I mean, the U1 gauge field is dual to a scalar, right?
That's right.
So can we see a 2+1 dimensional superfluid as a scalar?
Right. So yeah, because it's just this field here that I'm putting here. It's just your Goldstone field. Okay. Yeah, that's right. So 2+1 electrodynamics is dual to a superfluid. Okay. And what you would call the electric current in your electrodynamic theory are just like the vortex current in the dual picture. Okay. So actually, this rho and j is just basically the current associated to this, the current associated to those dots. I use this like a very like hand-waving introduction to superfluids because what actually I want to talk about is solids. But I told you that solid. How long do I have?
You have about 10 minutes. Yeah.
Okay. Counting the long break.
Yeah, you have 50 minutes.
Okay. Yeah. Okay. Yeah. So yeah, I argue that solids are superfluids. So then introducing like a solid fluid is technically a little bit more involved. But actually, I went just to focus on the vortices in solid, what I call a vortex. So in elasticity, there are two types of topological effects you can have. Okay, they are called disclinations and dislocations. Okay, a disclination is just nothing but basically like a conical singularity on the two-dimensional solid. The dislocation is like a localized torsion, but as you can see, so imagine that you have like, this is again like graphene, and you just like cut here, you introduce a triangle, and by this precise process, what you do is just basically substitute this hexagon by an heptagon. Okay, that heptagon is precisely the singular point. Okay, this is a singularity that has like an excess angle. Okay, that is like, so then basically this omega here, which is like the excess angle is the charge of your defect. Okay, you can do it with twice the angle. So then if you introduce a triangle, then that's what you would call like an anti-disclination. You see, we have here a minus. If we do it like the other way around, instead of cutting and introducing a triangle, we just remove a triangle. So then, as you can see, what you get here is a point defect that is a pentagon, and the charge then is plus omega, and you can get 2 omega. Now, instead of a pentagon, you have a square. You have only 4 atoms, and those are like like my vortices. Those are the topological effects. Though they are going to be like a not single value configuration in your elastic fields that I have not introduced yet. Okay. The thing is that in solids there's another type of topological effect that are called dislocations. Okay, and they're actually dipoles of these objects. Okay, dipoles of these objects. So this example, you see, so here there is an heptagon and a pentagon next to each other. So if you move around these points, by construction, you see that there will be a deficit angle or an excess of an angle. Actually, and then in this case, the way of detecting that defect is a different way. So you see that this thing in this drawing, we are seeing just like two parallel lines that the distance between them is just like one lattice side, But in that precise construction, when we go through the defect, now we end up having a larger distance. Okay, so for the dislocation, the charge is not actually a scalar. It's not a number, it's a vector. Okay, and this vector is called the Burgers vector, and it's basically, if you precisely as you can see here, if you try to go around a loop around this point, the loop will not close. The loop will not close, and the Burgers vector is precisely the vector you need to close the loop. And for that reason, at this location, it's just like having like a singular torsion in your sheet. I can skip. This is not important. Okay. Now, how can we put this in mute? The girl is here, but you have to. It's not me. It's not me. For sure. Give it a touch.
Yeah, it works. Okay.
Yeah. So yeah, the thing is that in an analog way to the previous example of the superfluid, you can take your theory of elasticity that I'm not showing, and you can dualize it in a similar way. Okay, and then the analog field to the Goldstone field will be mapped in some sort of like exotic gauge field that that is not important. The only thing is that that gauge field is going to be minimally coupled to the defects in the same way. Okay, and actually those defects, which are these things that those are things are going to be my charges, will satisfy a continuity equation of this form. Okay, so this is kind of like exotic continuity equation because as you see, so this rho here is the density of these objects here that I'm calling declinations, but then the current is a symmetric tensor, and then you see this equation has two derivatives, and as I'm going to argue like immediately after, this type of continuity equations are the conservation laws of the things that we are calling fractals. Okay, and so in other words, what I'm just like will try to convince you is that actually these things that these things like these declinations and dislocations are fractals and dipoles of fractals, which is like something that people is just that is kind of like a popular story in the literature right now. So this I can skip, and now let me just change gears a little bit, and let's suppose like let me just postulate this following. Let's suppose that we have a system with a conserved charge Q, but then in addition to the conservation of that charge, I say, okay, the first moment of this charge is something that is conserved also. As I'm just saying, Q has to be conserved, therefore Q dot has to be 0, but Q times R has to be conserved as well. Okay, immediately after, if you impose these two conservation laws, well, obviously R dot has to be 0, and then it means that that excitation cannot move. Okay. So let me stop. Oops. Can I stop it like? There is no way to stop it now. Okay, so just as you can see, so what this thing is doing is like, in principle, I said these things cannot move, but if you just actually imagine this as like a quantum particle, actually these conservation laws does not forbid the motion of that thing, thing that I'm calling fracton, this particle that has charge Q, as long as this thing emits some sort of like molecules that have 0 charge, but they have like dipole moment, which are, you see, this these things with blue, red are kind of like dipoles, and as long if in any step that particle emit a dipole, it can shift. And that's a way for that thing to move, conserving, not violating these conservation laws. Okay? But well, actually the thing is slightly more tricky, because if we if this blue line is just okay, if one of these particles that has momentum k, and these dashed lines are just, for example, these dipoles that this thing is emitting, just by analyzing momentum conservation and energy conservation, like in this is like in this process, this particle has emitted like n dipoles. You immediately after realize that okay, the change of the moment of this thing has to be proportional to the number of dipoles this thing emitted, and k0 is like the characteristic momentum of each dipole, and A0 is again like characteristic energy that each dipole is carrying, and it's the number of them. And then you see that actually, in order to conserve in that process, in order to preserve that, so two things can happen. It's like either if this thing is not zero, so then it means that either each dipole carries like zero energy or momentum, or this thing is self-accelerating. Okay, the system is just going to be self-accelerating. So then in principle that it looks like that should not happen, not even just from kind of kinematic reason, unless there is a way of kind of like exchanging very soft dipoles with the vacuum. So it means that the vacuum cannot be trivial. So if you have some sort of like a spontaneously broken phase, then in principle that would be possible. And then if you are in a phase where some of those symmetries are spontaneously broken, you could extract like a very soft dipole from the system, and then get like a very slow fracton that can move. That's kind of like the argument I went to. And then, okay, if you are like more careful, then if you consider two particles instead of one, then it's like very easy to realize that the dipoles can freely move everywhere. If this you have like a plus minus charge, this thing can freely move anyway in all directions. But then if they have the same charges, so they can move also, but with opposite velocities, and it will not violate any symmetry conservation. Okay, so you are interested in like long wavelength description. So I introduced, associated to this Q, Ds, and Ps, these local densities, okay, rho, and associated to the dipole. I'm assuming that, so if you have a density rho of fractons, then the total dipole moment of the system should be the first moment of that density plus the density of these dipoles. And this is just like the total momentum of the system written in terms of some densities. Remember that this is some region of space. By O, I refer just like to wherever, like the origin of the space I'm using. And inside this region, I have a certain amount of charge Q, P, and D. So if these three things change in time, it means that they have some currents that are just leaving the region, just very generic like arguments. So, and then it's like really easy to verify just by taking time derivative of these three things to conclude that actually the continuity equations have to have this form. Okay, so this is just momentum conservation, tau is just the stress. And then the time derivative of this density here, which is like the density of dipoles, is actually not conserved because it has to be conserved with the full thing. But then it relates that with this current J in this specific form. Okay, then important consequence. Okay, so I'm assuming that momentum is conserved, so my space is homogeneous, so it doesn't matter where I put my origin. I should be able to start measuring things from whatever point I want. So then you just imagine that I just shift this point O to this point here that I'm calling O prime by this vector R. Okay, by doing that, then relative to that point, the dipole moment will change. It will change precisely in this form because I just shift the origins. Remember my definition of my dipole. It's just like the first moment of the density rho times t. So then if I shift r, so then I just get this new value for d prime. So in other words, actually, what this thing is just telling me is just that charge somehow is like momentum and dipole are things that are charged respect to each other, and they cannot commute, and the bracket between the momentum and the dipole is it has to be the charge. Okay, so then it means that even though these charges Q and D from the beginning are just like internal charges, they have like this very exotic and weird property, okay, that they not commute with momentum. And since I'm like really out of time, I will just like start just concluding that I will not show the whole hydro theory for the fractons, but I told you before about the elastic the elasticity. I mean, all these elastic defects that they were fractons, but actually these conservation equations I derive don't have this form. Okay, but if you remember, actually I told you that that in the long wavelength regime, only the conserved things are the relevant ones. So this D is not a conserved quantity. Okay, so it means that if you wait long enough, this D should just like decay, should just like go to zero. And then when you are in that regime, you get that J is just decay. So you just plug this thing here, and then you get precisely the continuity equation I was showing before. Okay, this is a hand waving way of arguing that indeed the defects are captured by this symmetry. By the symmetry that I'm introducing, that is like this dipole conservation. So let me just skip this whole story, and we'll just show you the results. So what we did here is just trying to, in the same way we described this hydrodynamic fluid, this relativistic hydro fluid that I was talking about, just using the same principles and imposing all the constraints coming from symmetry and everything, trying to construct hydrodynamic theory. But well, there is this restriction between motion and fractons and this thing. But remember that I told you that actually, if there is some sort of like a superfluid phase, it's possible to have things can move in some sense. Okay, so this phase that I'm just going to show you is the phase in which dipole moment is spontaneously broken. And for that theory, at the lowest order possible in derivative, there is only one transport coefficient. If you remember in relativistic hydro, there were three: the shear viscosity, bulk viscosity, and electric conductivity. For this system, at the lowest order possible in derivative, there is only one transport coefficient. This J epsilon is the energy current. So then it's some sort of like thermal conductivity, this alpha. And then to have things like shear modes, you need to go higher order in derivative is like not super important. The thing is that then, so associated to this thing, there is no sound. So this type of fluids do not have sound, because as you see, so the longitudinal modes, the sound is in a fluid is a longitudinal mode. It goes like C k squared, and this C is a complex number, but this complex number, and there are three of them. There are, which are like these three colors in the pictures. Like we're not going in detail, but the thing is that actually, depending on the value of the conductivity, they can be like purely imaginary, or they can have like real and imaginary part. So indeed, if so, the hydrodynamic regime of this system is completely different to the hydro of like an ordinary fluid. Okay, there is no sound propagation, because actually the longitudinal modes have like this k-squared type of dispersion relation. So, well, let me just conclude here with these comments that you can read, and well, please ask me whatever you want.